I think we can start. More generators for the god of generators. Yeah. I got something yellow. We have zero viewer. Okay, I need to switch. I'm 5 minutes behind shadow. So, what I got today? I have a generator of signal. Very good generator. The generator is guaranteed to have distortion less than 1 in 1,000. It's a good generator. And I attached my generator to my nice digital scope. Frequency of signal is 10 kilohertz, 3 volts RMS. Yeah, you're missing yellow line. And nice yellow line is my generator signal. My scope is a digital scope. Yeah? Yeah. And my generator is an analog generator. And now take a look on one thing. I will change the time scale. I'm changing time scale. Oh, this one is nice. Do you see frequency? What's my scope showing? 6 Hertz. Do you see 6 Hertz? What's the frequency of signal? Did I change frequency of generator? 10 kilohertz. See, nice sign at 10 kilohertz. What's the signal with frequency 6 Hertz? Is it real? Yeah, it's too low. It's fake. The thing what we see is an effect called aliasing. Idea. I have my signal is, or let's say cosine omega t, nice harmonic signal. What's the function of digital scope? Digital scope takes measurements, take samples and display the samples. So this will be signal represented in discrete time, where tau is a sampling period. Like I draw this one, it's normal, it's simple, it's clear to everyone. Clear? It just takes samples and draw chart on samples. What's going on now? I have the same signal. Maybe I can switch. I have the same signal, but samples are taken with inadequately low rate. I have set of samples, but the samples are taken too slow. And what I'll see, and so on and so on and so on, I'll see something like a harmonic signal, yeah? But with a very slow repetition rate. You can also call it stroboscopic effect. Here, what we see, I may try to freeze it. Oh, I got it. See, very, very, very slow sine. If this signal would be some kind of process, it would be definitely distorted. Yeah? Yeah. And now I can ask a question. Let's say minimum of sampling rate, I play with the sampling rate actually to keep to keep system operational, to system being in somehow representative. The basic idea belongs to famous Nyquist. And Nyquist idea was quite simple. There should be at least two measurements per period to somehow represent adequate signal. So this means that sampling rate or discretization frequency should be at least twice and the maximum frequency of signal. Oh, you will like this. Nice sign. Except one tiny movement, frequency of 300 millihertz, while its actual frequency is 10 kilohertz. It's a clear example of aliasing. Here it is real, 10 kilohertz. I can attach an analog scope and you'll see. So, basic idea of so-called Nyquist frequency, if you have a digital system with sampling rate f sample, it can process anything, sound or I don't know, voltage, current and so on, with frequency it should be sampling frequency should be at least twice higher than the max frequency of the signal. And do what you want, but in your digital device, you need to include an analog stage, at last low pass filter. For example, this board from digital relay, here resistors, here condensers, they form a low pass filter to cut frequencies above Nyquist frequency. But definitely it's a it should be proved. And proof can be found in conjunction with one specific kind of role. There was one researcher, Catelli, and he worked with the role kind sine kx divided by kx. This should be. Such function form an orthogonal system and can be used as a base for Fourier decomposition. So let's assume that we have a signal what can be substituted with Fourier rho f power omega d omega. So let's assume what we have signal and GS is a Fourier transformation result of the signal. We don't need to limit ourselves periodic or non-periodic. Let's just assume that Fourier representation or representation in frequent space of the signal exists. And also, let's assume that signal occupies a limited frequency range. So we can assume that omega equals to 0 if omega is some kind of omega max. And also omega is less than minus omega. But this signal occupies a limited frequency range. This is quite reasonable for a real signal, not theoretical. In such case, we can do a funny trick. We can try to perform a Fourier decomposition on spectral function. Here, double omega will be some kind of period. So repetition period, it will be in frequency space, but we can, let's say in mass we can do it. We can substitute spectral function with kind of Fourier law. It will be a bit unorthodox row, but it should appear something like this. 1/2 sum from minus infinity to infinity. Okay. Some kind of harmonics amplitude. A power jk double T divided by omega max. Second, there should be no, and by omega. Here I use a Fourier row, but I have substituted time with the frequency. Can I obtain these Fourier factors? Who stops me? For this row, okay, it's a bit tricky, but I'm using frequency instead of time, but in abstract mass, for abstract mass sense, there is no difference. Function, argument, who cares? It will be, it should be 1 divided by omega max as a period. I should integrate to minus omega max to omega maximum. My spectral function, a power t p divided by omega maximum. Here should be omega and the omega. it's a complex value. Remember what I started with, what my signal was 1 divided by double P, integrate from minus infinity to infinity, as omega a power, sorry, it should be j omega time the omega. Can you compare these two? They are very simple. In both cases, I have spectral function and a power, and both are integrated in frequency. Yeah? This means what I can write as double P divided by omega max signal values at minus k P divided by omega max. Or remember, for sampling interval for tau, because we want, okay, I can take a tau, is P divided by omega or delta T. Okay, let it be, to not to confuse. So I can write here double sum at minus delta T. Now I can rewrite my spectral function in a bit different way. I can rewrite spectral function as sampling interval sum from minus infinity to infinity minus delta T a power not k delta T omega. Let's simplify it. Delta T sum minus infinity to infinity signal values k delta T a power minus j k delta T omega. Whoa, 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 whoa. See, we have here a discrete form to obtain our spectral function. I would like to use this discrete form in inverse Fourier transform. I will substitute this into our let's say starting position. What signal can be substituted with it, or signal spectral function is equivalent of signal. If I do so, I will be able to write 1 against double P minus omega max to omega maximum delta T sum by K tends from minus infinity to infinity K delta T at power dot omega K delta second here should be K delta T at power minus what? One moment, I will make a house here because I need to take samples at power dot omega. This one can be rewritten. 1 second. Where is my mistake? Oh, this one can be rewritten as delta T divided by P sum minus infinity to infinity K delta T. Who write delta like this? Sinus, no, omega max T minus K delta T divided by omega max T minus K delta T. Yeah. Here I have a row. Set of sine kx divided by x, kx. It's a set of orthogonal functions. It's a base for Fourier, another form of Fourier row. For this function, this kind of function, it's very easy to calculate. What? Such kind of function. So if I have f kind of t, let's say sine of kt divided by kt, it will have unity value when k double p divided by omega max. And equals to 0 when time, here I have p divided by double f max, and equals to 0, wait, yeah, 1 divided by 2 f max. So this means what whole Fourier row at a time k being k1 divided by f max, the whole row will degrade to one member equals to the value of signal at tk. But the row where the row we are talking about represents signal fully. That's me. What? My signal can be fully represented if sampling interval equals to P divided by omega max or 1 F max. This is necessary sampling rate. This is necessary proof of Nyquist idea. If your signal spectrum contains components starting from, let's say, omega 0 to, let's say, I don't know, m omega 0, sampling rate omega t should be at last 2 m omega 0. At last twice. That's what I wrote. It's boring, but it proves what signal can be fully represented if this is delta t. So sampling rate should be at last twice the signal frequency, or delta t should be at last 1/2 of the period. Of max of frequencies. It's 0.1. It's a very important thing. Why it's important? Because it sets you a benchmark or required performance rate for your digital system. Your digital system should be able to process signal with the frequency at least twice higher than the highest of signal nature frequency. If you would like to process sound with the frequency up to 20 kilohertz, what should be sampling rate? 40, twice. Actual PCM rate is 44 kilohertz. Then you can compress. You can perform compression because this sampled signal contains, let's say, excessive information. But you need to take samples at a frequency at least twice higher than the maximum frequency of processed signal. More interesting thing, we can find another interesting thing if we analyze in frequency space. Okay, let's assume what we have a signal in frequency, let's say area from omega min omega to omega max. We have a say narrow band signal in which delta omega is omega max minus omega minimum. Omega 0 central frequency is max plus omega divided by half, and delta omega is much lesser than omega 0. We are dealing with a limited frequency range signal. Here, I will draw an omega max, omega min. Positive frequency, and since spectral function is such thing where we have a negative frequency range but conjugated, so this will be minus omega min minus omega max. This area is conjugated to the original. It's all because Euler's formula. Because Euler says what? E power j alpha plus e power, minus j alpha by half. Because of Euler's formula, in mass definition, we always have a conjugated, let's say mirrored spectral function in negative frequency. I'm drawing the chart as a function of frequency. Here I have two areas. Let's say it's GS1 and this is GS2, where GS2 is a conjugation of GS1. And my signal spectral function is a sum. Is it clear? Who don't know what it's conjugation? Who knows what's mean conjugate? One. Conjugate. What's the meaning of this symbol? What the silence? Let's say you have plus 1 and plus j, so square root of minus 1. You have complex value x, a, b. So x is a plus j b. Exist, draw it in this one, mirror x, a minus j b minus b. Mirrored or conjugated. This one is conjugated. If this angle is phi, this angle will be minus phi. So, returning to our spectral function. We can try to create a periodic function from omega in such way that it will go as original signal spectral function. S1, S2, conjugate to S1. I would like to create a periodic function something like this. Period here will be double omega. So what I need to do? I need to select delta omega to be double omega 0 divided by n. When n is a smallest integer and not the smallest non-odd integer dividing double omega 0 by delta omega. So I need max int max not odd non-pair int from this division. This allows me to decompose GP into Fourier road. I will use as a period double delta omega. So I will be able to substitute my periodic GP with the Fourier road that should start from minus infinity, a to infinity, a key complex a power k p divided by delta omega multiplied by omega. If I do so, I'm expecting what I can find these factors. I'm expecting it. It's a tricky thing because I am in area of complex and spectral function. Remember, spectral function is a complex. I cannot work with models. I need to work with full complex. So it's a bit tricky. But if we deal, let's say, in pure mass, my original signal can be substituted multiplied by minus omega max minus omega min my periodic function at power j omega t, the omega plus omega min omega max again no omegas at power j omega e, yeah, omega e the omega of. If I substitute this term with the row, I'm assuming that this row is existing. What I'm unable to get these factors. As we saw previously, I can use sine kx divided by kx. In this case, I will get quite specific row. One moment, I will write it. So my can be represented as a sum minus infinity to infinity half p divided by delta omega here should be sine of delta omega by half multiplied by t minus k p divided by delta omega divided by delta omega by half multiplied by t minus k p divided by delta omega. And this should be also multiplied by cosine t minus k delta omega and one missing. Oh yeah, omega 0. Blah, 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 blah. Very heavy formula. But in this formula, all these parts are elements of sampling. Look here, all this is known, and these are only, let's say, derivatives of sampling. Actually, we deal only with we only deal with samples and frequency. Since all this is known, the only unknown part is this. Yeah? What does this mean? This means what my continuous signal can be fully represented if here I'm speaking in frequency space. If I take samples with the double frequency of the signal. Here, again, omega discrete is double delta omega and everything goes. Because only this term is unknown and placed. Signal can be fully represented with values of its spectral function taken with the step of double or in step of double frequency. There is one tricky moment. You know, it's funny, but if you take in this form, if you take a higher sampling rate, you will get a negative result. If you take as written like this, it will be a funny moment. You have a frequency scale 0, 1 delta omega, double, 2 delta omegas, 3 delta omegas, and somewhere here is your omega min, omega max. Very fun. But if you take omega discretization above 2 delta omega, you will have this strange omega being m omega d, where m is an integer. And problem, this part from the whole spectrum, this part and around it, because we need to deal with real tolerances, this part will disappear from the result. You cannot, if you have the such case, this means what part of your signal spectrum. Why we're talking about this? Let's say it's you do it what? You have, for example, radio broadcasting. You have sound, then the sound is transferred to, let's say, I don't know, 100 megahertz and transmitted. You have a digital receiver. Digital receiver takes samples. If you have a sound, you take, you do this basic approach, and you have, for example, sampling rate above something like here. In your signal spectrum, what you need to process, you will have this possible. We will have the spectral line being integer multiplied by discretization frequency, and it will be distorted. That's why in series processing different approach can be used. Since one is a conjugated guys to, you can use such form. 1 divided by double P multiplied from minus omega max to minus omega min conjugated minus omega at power j omega t d omega plus omega min to omega max s1 omega a power j omega d omega. Here, this function can be decomposed or represented as a Fourier law based on sine decomposed. This will lead to specific rho. This rho will be, so can be represented as a sum from minus infinity to infinity half double P divided by delta omega sine delta omega by half t minus double p divided by delta omega multiplied by cosine of omega 0 t minus k double p divided by delta omega minus, I will continue. Nice small formula. Can I erase? Yes. Wait. It's only looks drastic. It's not so infinite. Sine delta omega by half t minus delta omega by стави means moment this will be correct divided by delta omega by half t minus double p by omega multiplied by sine of omega 0 t minus double p divided by delta omega. One more correct. So here's idea what? I can walk around this problem of this not rejected but repressed frequency by performing sampling not only on base signal but on conjugated signal. It's a tricky thing. If your base is a sine or cosine, you can obtain conjugated signal simple by shifting on the half of period. You can obtain conjugated signal. I will talk in detail when we will speak on Hilbert transform. And if we speak on Hilbert transform, we see it's introduced an idea of conjugated signal to the original signal. It can be obtained with analog technique, and if we perform a sampling both on signal and its conjugated twin, we will get everything will be fine. Because we should not exactly match sampling rate to the signal frequency. I would like to show one little example, numerical example. 1 second, I will find my example. I have, oh yeah, here it is. I have my example. 1 second, I will connect my Yeah, I need to make it visible to my viewer. So I have an example of discrete Fourier transform application. Very simple example. Here it's written in syllab language. Maybe I will take this where it's needed. Here. I will explain it a bit later. Okay, what I got here, what you see in front of you, it's a table of signal values. Within one period, values of signal are taken and stored as a table. This one measures this table, and what this? I have a number of elements. It's just for automation. Here I'm filling the array of omega t with a simple cycle from 1 to machine count 1, 2, 3 up to n, which is number of these elements. I will need it here. Then I will need it to draw a chart. This part. This part what's this? Sum equals to 0, not important, n harm, number of harmonics. This part is nothing else when discrete time Fourier transform. So if I have a signal being a periodic signal, I can substitute it with Fourier rule plus sum 1 to up to infinity of cosine double p plus sk sine of k double p. That's what we talk about multiple times. Yeah? How can I get this sine and cosine factors? With the help of discrete time Fourier transform. Sorry, I want S I cosine I minus 1 K double P divided by time. Sine factor will be by n, sum I into 1 to n, S I, sine of I minus 1, K double P divided by. That's what you see here. You see? This row, this small part is for DC component. Simple average, sorry. Here it is. Simple average to get DC component. Maybe I will temporarily cut this off. What I got next? I need to check, did I perform this Fourier transfer correctly. How can I check it? If I perform a synthesis, if I realize my first formula, what should I get? Nice line, yeah, which is equal to my signal at a measurement point, yeah. So here is draw of nice line. Oh, this should be familiar. This formula I wrote. And I'm drawing a chart here. This one is results of synthesis, and this one original table. They should match. Yeah? Yeah, let's check. Do you see what I see? The green dot is original. The blue line is result of synthesis. Do they match? Maybe here. You can see, yeah, it's a small difference. Tiny difference. So, appears what I perform a Fourier calculus correctly. Yeah? It's tiny. This should appears would be 41,110 minus, and this 112, so here is 11. 1 in 1,000, my precision appears to be, yeah? This means what? Quite nice. Here I'm also calculating average and effective or RMS of my signal. You can see it's very easy. And what kind of chart? What's this chart? Sorry. I would like to see components. Here. Take a look. Original points, synthesis, base harmonics, second, third, and so on. Funny. As I show, I started with Fourier row. Ideal harmonics in some form. Do you believe what all this line, if you sum them, this nice ideal line, form a blue line? They do. Ideal components, if summed together, are forming this nice blue line. But why I'm showing this? Just to speak about discrete time Fourier transform? See this number? Number of harmonics. If I put here 20, what will happen? Wow, wow, wow. Who can explain? I just tried to make it more precise. Instead of 10 ideal components, I attempted 20. And what happened? You see what it's distorted? Results is a failure. Why it's a failure? Because 20 samples is not enough to maintain Nyquist frequency. Results is distortion. If I check 19, it works. You see, it works. if I take, for example, 22, oops, everything ruined. Because I didn't obey the rule of Nyquist frequency. I should have enough samples in period to maintain rule, but sampling frequency, or 1 divided by distance between samples, should be at least twice of the highest harmonic. Highest I can get here is 19. And the moment I attempt to calculate harmonic number 20, yes, it's a complete disorder. It's a rule of Nyquist frequency. To process signal with frequency up to F max, you need to take samples with the frequency double F max. If you not do so, your sound will be distorted, your image will be crippled, your, I don't know, you can try to control your plane and your plane will crash. Because you will get this oscillating noise in your control channel. Everything will fail. It's what it tells you. It says you it sends you a bottom line for your hardware performance. If your system works with frequencies up to 1 kHz, be so kind, maintain sampling frequency at least 2 kHz. Or nothing can be happen. And another way, if you have if you have a representation in frequency space, MPEG compression works in frequency space. You cannot restore your signal if your sampling rate in the frequency, again, you need to keep this 2 not in mind. It's, how to say, gold written in a sky. If you have a frequency range delta omega, be so kind, perform a sampling in frequency space to delta omega, or everything will fail. "20 harmonics and will come to failure. Nyquist frequency. It's a 10. Works. Yeah. Maybe some questions? This mass looks heavy. It looks heavy, but you only need to keep in mind this number 2. Frequency should be twice. All other, it's a, how to say, foundation. You need to prove. Okay. If there is no more questions,